Hi everyone, I'm Dr. Tanya and I'm with the Outer Space Institute, which is run out of the University of British Columbia. Before this, I used to work for Arizona State University's Space Technology and Science Initiative, or New Space Initiative, where we worked on partnerships between commercial space companies and the academic and government sectors to see how we could spur innovation across all three of those things. I also now currently work for a commercial Earth observing company called Planet Labs. And today we're going to be talking about the new space sector in general and how we can apply some of that technology beyond Earth and some of the ways that it's already been applied right now. So if you're not familiar with the term new space, this was coined back in 2004 to describe this new agile aerospace sector that was starting to pop up. And in this time between then and now, this sector has completely revolutionized the way that we can approach space exploration with things like rapid prototyping, lowering launch costs, smaller satellite form factors, which ties into lowering launch costs, small satellite launchers, pushing toward maximizing reusability of components to bring the costs down, and utilizing commercial off-the-shelf components rather than custom one-offs. One of the biggest ones that you guys have probably heard of before in terms of new space are the innovations in the launch sector. So SpaceX has really changed the game here. With things like Falcon 9 and Falcon Heavy, it's brought launch costs down from the hundreds of millions of dollars range to sub 100 million in some cases, depending on whether you want to reuse the boosters or not. This greatly enhances access to space so that companies that might not have the resources to launch on, say, an Atlas V or a Delta IV Heavy now have these options. And they also have rideshare options with other things that might be flying aboard a SpaceX rocket, for example. There are a lot of comparisons of these rockets to things like the Space Launch System that's currently under development. And if you look at something like a Falcon Heavy, even though the amount of payload that it can take to low Earth orbit, it's very small font at the bottom here, but it's about 64,000 kilograms to LEO for Falcon Heavy and 130,000 kilograms to LEO for SLS. The cost difference between those two things is quite extreme. So there's talk of, is it more cost effective to just launch things in smaller pieces rather than needing a big rocket to launch fewer large pieces and assemble things in orbit? But this is definitely something that will come into play when we're looking at how we're going to build rockets on the moon or Mars, for example. You don't have a ton of resources that are there available to you. So figuring out how to reuse as much as you can and keep those launch costs down are going to be really key, as well as keeping launch costs down so that we can launch more missions into the solar system with the resources that we have here on Earth. Reusability is one of these big things that has come about with the way that SpaceX has been doing things. And a lot of this has come from being able to recover both the boosters and the fairings in a lot of their cases for the launches. The booster accounts for about 60% of the total cost of a Falcon 9 rocket per launch, and the fairings are about 10% of the total cost of the rocket. So if you're able to recover one or both of these in a launch, this helps keep those costs down. And the the launch cadence has also been increasing rapidly as well. In June alone, SpaceX had 4 slated launches. 2 of those have already happened. There should be 2 more between now and the end of this month. One of them is actually tomorrow evening if all goes as planned. So we're seeing huge spikes here. And then just looking at the timeline of agility and how this program was developed, between 2010 and 2020, you go from the debut of the Cargo Dragon from SpaceX to a crewed launch aboard a Crew Dragon. And they've had a lot of innovation and success in that intervening 10 years. Comparatively speaking, looking at something like the Space Launch System or SLS, which was given the green light in 2010 and now in 2020 still has not launched, it shows you the difference in approach between the commercial sector and sort of the more traditional way that NASA has gone about things. I shouldn't just say the traditional sector, but specifically the agile aerospace sector, because you are still working with commercial partners under the original NASA model. It's just a different way of approaching how these missions are run and how the tech development goes along. And obviously, the SpaceX Crew Dragon launch was successful. It had not launched yet at the time of the tweet in this previous message. And the fact that that this was successful, I think says a lot about the risks that NASA is willing to take nowadays and the innovation that they're willing to push forward with. So I'm not sure even 5 years ago, people would have expected that crew would be launching aboard an entirely commercial craft like this before, and certainly not having SpaceX beat Boeing to sending humans into space after their return to flight from the space shuttle. So this is really exciting to see that NASA is putting a lot of faith in this new space commercial sector to the point where they're trusting astronauts' lives aboard these missions. And I think that really bodes well for the future of the commercial sector as we start to move beyond the limits of just operating in low Earth orbit. And we can see with the Crew Dragon example, some of the cost savings that the new space approach has afforded us. While these two systems were being developed, the Boeing Starliner crew capsule and the SpaceX Crew Dragon capsule, you can see the difference in the red number above both rockets. This is the total paid over the entire lifetime of the commercial crew program from NASA. The SpaceX development costs were $3.14 billion compared to Boeing's costs at $4.82 billion. So there's a significant cost savings here with the way that SpaceX approached this. In comparison, Soyuz seats were anywhere between about 55 million to 80 million. They got more expensive over time in terms of buying crew seats aboard these missions. And then the cost from Boeing ended up being even more than that. So that's part of what led to selecting SpaceX for flight. But again, this really demonstrates the differences between these two models of approaching technology development for space. Small launchers are another big innovation that can help us in terms of planetary exploration if we want to start utilizing small satellites, which we'll go into in a bit more detail later. There are companies right now like Rocket Lab and Virgin Orbit that are developing launchers specifically to launch CubeSat and SmallSat type satellites, which gives you the advantage of a lower price point, and you don't have to wait for a rideshare opportunity with a larger satellite that happens to be going in the right trajectory or to the right orbit that you need for your satellite. So there's more flexibility there. Right now, the Rocket Lab Electron is the only one that's really actively launching in terms of small satellite launchers. Virgin Orbit has had some successful tests with their launcher one so far, but we'll wait and see how that goes. The biggest innovation in sort of the new space sector that really applies toward planetary exploration is the development of CubeSats and SmallSats. And these really started as a university experiment and they were very primitive in terms of capability, just radio transmitters that could ping ground stations and things like that. But now at this point, they're a proven technology in low Earth orbit, and NASA has established things like the Simplex program to actually fund the development of interplanetary CubeSats and SmallSats. So they're really adopting this well. And the upside to these, especially in the CubeSat form factor, is that you're introducing some kind of standard. So instead of making these custom one-off missions for everything that you want to do in the solar system, you design to this standard so that it's easier to utilize potentially commercial off-the-shelf parts, or at least draw from the heritage of some of those parts if you do need to make specialized technology for the specific investigation that you want to do. And then you can take advantage of things like ESPA rings for your launches to try and keep your costs down, because you are able to share with other missions that are flying into space. We've seen a lot of CubeSats and SmallSats being used in low Earth orbit right now, but these are used in ways that have applications beyond Earth as well. Planet Labs currently operates the largest fleet of Earth observing satellites. We have 150 CubeSats and 18 SmallSats that image the Earth every day. And these are land focused. So they image the land mass of the Earth out to about 15 kilometers away from the shore anywhere. There's another company called Spire that has a constellation of a little over 70 CubeSats at this point that are focused on maritime monitoring. I'm sure everybody at this point has heard of SpaceX Starlink, which right now has over 4,000 satellites in orbit, small sats. So these are larger than the CubeSats in this picture here on the right. These are focused on telecommunications. And to compare this to non-commercial constellations that are operating in Earth orbit, the largest constellations right now are 24 satellites from GPS constellations from the US, for example. So the commercial sector is getting really good at building and operating these large, complex, multi-satellite constellations. And these are things that we might be able to utilize beyond Earth. And we'll talk about some of the missions that have already flown and things that are proposed in a few slides. So Starlink is the biggest of these proposed constellations. They are still building it up. Each little streak of light that is moving horizontally in the image on the right here, that's a view of a Starlink satellite from the International Space Station. And there's an inset at the bottom here, which is an artist rendering of what the Starlink satellites look like in orbit. The goal of Starlink is to provide internet access in areas where laying fiber optic cable is not economically viable. And since they're in low Earth orbit, you need a lot of them to get full ground coverage. Regardless of what opinions you might have about Starlink and the way it's been implemented, because there are definitely some issues there, we can acknowledge that the model of this definitely has telecommunications applications for looking at the moon and Mars. We don't necessarily have the resources in those places to lay a bunch of fiber optic cable, for example. It would be extremely expensive, very complicated to do. You don't have a lot of excavation equipment. You might not even have the materials you need to make the cables, and it would be quite expensive to get them from Earth to wherever you're going. So being able to utilize small satellites that you could rapidly build and launch and operate would work really well in these environments beyond Earth. There are also a lot of opportunities for interplanetary CubeSat applications. Tech demonstrations is a really good example, which NASA has already done and we'll talk about soon. Using them as sort of expendable probes working in tandem with larger motherships. So if you need something like flying into the atmosphere of Jupiter without destroying your entire mission, you might be able to use it for something like that. You could also have disaggregated missions, and I'll show an example of that a bit later as well. And if you do this, you have a chance to lower your cost and risk posture, as well as giving you more options for your concept of operations for these missions. This also gives you a chance at cheaper spacecraft and cheaper launch costs by going with something like a CubeSat or a SmallSat form factor, which means more opportunities for exploration across the solar system. If we're not funneling $2.5 billion into a single mission every couple of years when those opportunities come around, it might make it so that we could spread the wealth throughout the solar system a little bit more. You know, I know the Venus community would really love to see some missions there. I would love to see more missions to the outer solar system like like Uranus or Neptune. And looking at things like this instead of these all your eggs in one basket flagship missions might be a concept to start looking at so that we can at least get some science return. You're not necessarily getting everything that you want, and it might not be the highest quality data. It won't be perfect, but in a lot of cases, less than perfect data is still better than no data. And this is an example from the Mars Reconnaissance Orbiter where having instruments on different platforms would have actually served us quite well as an example for something like a disaggregated mission. These are images from the Mars Color Imager, or MARCI, aboard MRO. And MARCI has a 180-degree field of view, but it can only operate up to a certain slew angle off of nadir. And then there were other cameras on this mission that were designed to work up to 30 degrees off nadir. And so anytime that the slew angle would change too high, you actually couldn't collect data with this instrument that was meant to be sort of an always-on taking pictures in the background mode. There are other instruments on MRO that have the same limitation. They can't operate over a certain angle off nadir. And so this has led to some really complicated solutions for the concept of operations to try and get all these instruments to work in tandem with each other. But if these were perhaps on different platforms, simultaneously imaging CubeSats or SmallSats, for example, you might be able to get all of the data that you wanted without so many gaps from each of the separate instruments here. So everywhere here that you see gaps are places where MARCI was unable to image because the spacecraft had slewed so that other instruments on board could take data. Whoops. So I mentioned before that CubeSats would be really great as tech demonstrators, and we have already done this for Mars actually with the Mars CubeSat 1 mission, or MARCO. And these flew as a pair of CubeSats on the way to Mars with the InSight lander, and they were deployed partway on the way to Mars. and they were designed to act as telecommunications relays, because the way we land things on Mars right now generally involves landing something, trying to schedule it as well as you can with the orbiters that are there that might fly over to get the telemetry to send them back to Earth to make sure that everything is going properly. This way, the CubeSats were able to act as the relays between the InSight lander and the satellites that we already had operating around Mars, and they worked successfully. And these satellites incorporated some commercial off-the-shelf parts, like the camera that took the image seen here, which was from a company called Gumsticks. They make basically cell phone style cameras, but you can take them and pop them into a CubeSat. Obviously, this image is not fantastic quality compared to what we're used to seeing on Mars, but imaging was not the main goal of this mission. This was basically to say, are we at Mars? Yes, we can see Mars in the frame. So again, learning to live with data that is acceptable for your needs, even if it's not perfect, with the ability to reduce your costs significantly. And this is something that we might have to learn to operate within under new parameters of exploring the solar system with planetary missions, to be able to take the most advantage of the technology available to us while also reducing the costs and potentially getting more missions for everybody at the end of the day, which I think we would all love. So the MARCO satellites are a pair of 6U CubeSats. So a U is 10 by 10 by 10 centimeters, plugged into this standardized form factor. So you can see how small it is here. And one of the concerns that's been raised about CubeSats quite frequently, at least before MARCO was sent along, was the fact that these are not heavily radiation shielded. So there wasn't necessarily a lot of knowledge about how well these would survive a travel through deep space and the radiation environment on the way to Mars and then flying past Mars. But all of the components seem to have held up and everything operated as planned. So you might be able to get away with missions like this, even if you don't have a ton of radiation shielding, depending on what the goals of the mission are and the lifetime that you're expecting of these particular satellites. I mentioned before, NASA has started this Simplex program to fund the development of CubeSats, both in Earth orbit and beyond. Some of the ones that have been selected include this Lunar Flashlight mission and the Lunar Polar Hydrogen Mapper, or LunaMap, being developed out of ASU. But in these cases, the CubeSats that are being developed under the Simplex program are still extremely expensive compared to the costs that are coming out of the commercial sector for satellites like this. The Simplex cost cap the first time around when NASA rolled this program out was $7 million. But from what I've been told, a lot of missions had trouble staying underneath that cost cap. And so the next time around, they increased the cost cap to $35 million, which sounds inexpensive compared to most NASA missions. But just as a comparison, the Indian Mars Orbiter mission, which is a full-size satellite with multiple instruments on board, was only about $33 million. So in the grand scheme of space exploration, $35 million is still quite expensive. And compared to how much these private companies are making CubeSats for, it's definitely very, very expensive. So there needs to be some more adoption on the NASA side in terms of understanding how inexpensive CubeSats can be or should be, and the paperwork process and the testing process that goes along with these, because it's definitely quite different from what you would necessarily want or need to put into a $1 billion flagship mission, for example. SmallSat Radar is the new hot thing in the new space sector lately, it seems, because traditionally space-based radar satellites have been large, heavy, and very expensive because of these two things. They're also quite data rate hungry and power hungry. But there's been an explosion of commercial radar companies recently driven out of the geointelligence sector. You can look through clouds, you can pick up the wakes from ships, things like that. So we have companies like Capella, IceEye, Predasar, Burlab, ExpressSAR, all building these smaller form factor satellites, trying to get it under 100 kilograms compared to what we're normally seeing, which radar satellites are typically well over that size. And these obviously have a lot of applications beyond Earth, looking at places shrouded with atmospheres like Venus and Titan, and looking at ground penetrating radar options for Mars so that we can map out the subsurface distribution of ice for in situ resource utilization, and deciding where we want to send humans in the future to make sure that we can send them to places where ice is easily accessible at the surface or near the surface. There are also, related to this, a lot of LiDAR applications beyond Earth as well. LiDAR has typically been a very big, bulky, heavy technology. The Velodyne LiDARs that are typically used in like really high fidelity applications can cost about $75,000. But now you see LiDARs on a lot of self-driving cars, for example, because they're really good for the ranging and mapping out the area around you. And so the self-driving car sector has really driven these costs down through things, or through companies like Uber, the Toyota Innovation Lab, working with different LiDAR startup companies. So they've managed to get the cost of these things to below $1,000. And the goal is to get, at least for Velodyne, they would like to create a commercially mass-produced LiDAR at a price point of $200. So these prices are being driven way down for sectors that have nothing to do with space, but we can use these applications for something else. Autonomous rover navigation is one big thing. The example here on the right is from the Canadian Space Agency's Mars Exploration Science Rover, or MESR, which has a LiDAR mounted on it, and it takes LiDAR scans around it in the Mars yard at the CSA, which is what this map is from. And from this, it can create internal maps of terrain traversability. So it can recognize whether the slopes are safe or not for the rover to drive over. And if we can incorporate something like this into a rover, maybe on Mars, or maybe if we wanted to go beyond Mars somewhere where we don't necessarily have the time or ability to get a lot of imaging before we can pick a landing site, we could go to one of these places and have the rovers do a little bit of navigating on their own, being able to pick out the areas that are safe for them to drive on or not. Laser altimetry is also obviously a huge application. We've sent laser altimeters to multiple planets and moons in the solar system at this point. So being able to get the cost down for those as well. There have been CubeSat-sized LiDARs developed particularly for asteroid prospecting, for asteroid mining applications as well. And so having small form factor LiDARs can be utilized for space exploration beyond just this commercial application of asteroid mining. But probably the biggest thing that's been on everybody's minds recently are commercial lunar activities, with the announcement of the Artemis program from NASA to send humans back to the moon by 2024 and establish a long-term presence by 2028. But NASA acknowledged that they can't meet this ambitious timeline without help from the agile aerospace sector. And so there's been a huge call from that sector to have input on these. And one of the big programs to come out of it is the Commercial Lunar Payload Services Program, or CLPS. And this program seeks payloads that advance capabilities for science, exploration, or commercial development of the moon. And so far, they've selected 14 commercial partners with $2.6 billion allocated to this program through November of 2028, so when they would like to have that established long-term presence. And the funding at the moment is pretty much solely focused on payload delivery to the lunar surface and other things supporting the Artemis program specifically. So they very recently, all of time's blurring together in quarantine, so I can't remember when it was at this point, a month or so ago perhaps, NASA announced the 3 selections for further development of Artemis human lander platform systems. The Dynetics team that they selected is a consortium of about 25 different companies, including Maxar, Sierra Nevada, Telzalina. So some of the names that have been in space for quite a while now. SpaceX, they selected their combo of the SpaceX Starship with the Super Heavy launcher, which was initially developed or envisioned by Elon Musk for Mars, but it has lunar applications as well, and we'll talk about Starship more a bit later. And then the national team is a group combining Lockheed Martin, Northrop Grumman, Draper, and Blue Origin. So you have some of the, we call old space and new space actors playing together. With the national team model, you have the Ascent element from Lockheed Martin based on technology they developed for the Orion capsule. Northrop Grumman has developed the transfer element based on the Cygnus capsule that goes to the space station. And then Blue Origin's descent element is based on the Blue Moon lander and their BE-7 engines that they've been developing for several years. Because Jeff Bezos actually announced a Blue Moon lander from Blue Origin long before the Artemis program had ever been announced. This was developed specifically to be able to transport about 8,000 pounds of payload to the lunar surface, or 14,000 pounds if you give it some larger propellant tanks, which is more like the arrangement you see on the selection here for the Artemis program. And again, before Artemis was selected, Bezos had already announced that he wanted to try and land Blue Moon on the lunar surface by 2023. And then once Artemis was announced, he threw his hat in the ring in terms of letting Blue Origin be one of the players for this, and said the only reason that they would even be able to potentially meet the 2024 deadline for returning humans to the moon with the Artemis program is because that they had already been developing the technology for Blue Moon for years before this program was announced. So again, the fact that the commercial sector was already on this was incredibly helpful, and we'll see how these timelines pan out as we move forward. Recently, the Artemis Accords were also announced, and these are heavily inspired by the Outer Space Treaty of 1967, establishing the peaceful uses of outer space. Unfortunately, it is a voluntary set of recommendations. It's not legally binding, but the things that it calls for are things that are in a few ways good for the commercial space sector. One, peaceful use of outer space, obviously. Releasing of scientific data, which could encourage maybe the development of scientific instruments to go aboard missions that these companies are developing. The development of international standards for interoperability. So this ties into things like universal docking at the space station, for example. They want to make sure that everybody can play nice together on the moon. And if you have something like a rescue operation that you need to happen, interfaces will work well with each other, regardless of what country or company that you're representing on the moon. They want responsible disposal of orbital debris, which again is a hot topic in terms of low Earth orbit right now, but we want to be able to take that technology and apply it elsewhere as we start to develop a human presence in these places, or just send more missions to these places to make sure that we don't end up with an orbital debris problem somewhere else. They also heavily lean on in situ resource utilization. So that's another opportunity for companies to develop technology relevant to that area. So mining tech, prospecting tech, processing tech, all sorts of things in that regard. There are also commercial aspirations toward Mars and applications for some of this new space developed technology that is in the works for future mission prospects. SpaceX Starship is probably the most well-known commercial endeavor with Mars as the end goal. Like the proposal that they have for the moon, this is a combination of the Starship vehicle, which is shown on the right here, with their super heavy launcher, which has yet to actually launch. And this was designed with the goal of long-term human presence on Mars. They want to send a bunch of these ahead of time, refuel them on Mars, do fuel generation on Mars, and basically have this taxi system going back and forth with fleets of starships. They're designed to be fully reusable, which is going to be extremely important beyond Earth because resources are extremely limited. But it also has Earth-based applications as well. This particular rocket can carry payloads larger than James Webb Telescope to orbit in a single launch, and they can dock with the ISS, so there's some flexibility there. It might be used for crewed lunar missions with the Artemis program, and they're aiming to get the launch costs lower than Falcon, which if they could do that would be a humongous game changer for something that can carry this much payload into space. But they're still in the testing phases. This is very preliminary. We'll have to see what happens as the starships are developed. And like I said, SpaceX has this view of wanting to have millions of people living on Mars with these bases and multiple starships flying all the time. But the one hindrance in their plan is that they aren't planning on developing any of this other technology. One of the refrains that came up quite often during the landing site meetings for Mars that SpaceX held a couple of years ago was that they would just say, we're just a transportation company. They want help from other sectors to develop the other technology needed to actually build out what would be on Mars. So that's a call to the rest of industry there. It might also just be a little bit of a cop-out, not wanting to actually develop those things themselves. But if there's a way to work together and find funding for these things, this opens up a lot of doors here in the realms of things like eclipse systems, so life support, 3D printing to create building materials, to create anything that you might need for repairs, maybe even textiles, because you're going to need to be able to maintain your spacesuits and have things to wear on Mars. Food science and technology, so how do we make sure that we have nutritious food that is also satisfying for people to eat if they're going to live on Mars or the moon for extended periods of time, because you probably just don't want to live the rest of your life on rehydrated food packets. Medical technology, which has tons of applications here on Earth, technology that you develop for the space station or anywhere beyond that can be used in remote medical applications here on Earth. Telerobotics, so operating rovers or other types of prospecting materials from a distance anywhere on Mars. Power systems, solar power, potential for developing more efficient nuclear power systems. Obviously, power is one of the huge limitations in space exploration, so innovations on that side could be extremely useful in space, but also have Earth-based applications to make power more efficient here. Mining technology, again, for that in situ resource utilization. So the actual, what are we going to do on Mars in terms of backhoes and drills and prospecting and things like that. Virtual reality applications for anything from training materials to keeping people sane in isolated environments. Trying to develop low latency communication systems like optical comms, so that we can also increase the data rate and data return from these deep space missions. And then sustainability tech is going to be a huge thing because, again, in resource limited environments, you want to make sure that you're getting the absolute maximum return out of anything that you have with you or anything that you've been able to mine out of the ground. And there are probably a ton of other sectors that I don't have listed here, and some that we might not even realize we need or have the ability to address until we start actually practicing and going out on these missions. So NASA is not just embracing the idea of CubeSats in terms of Simplex missions, but they're also adopting the idea of these complex multi-satellite constellations beyond Earth. And one way they've done this is through a concept mission that was selected for the most recent Planetary Science Decadal Survey study called the Mars Orbiters for Surface, Atmosphere, and Ionospheric Connections, or MOSAIC. I'm one of the team members on this mission proposal. And this is a fleet taking advantage of SmallSats, CubeSats, and traditional satellites with this disaggregated constellation so that you can have a bunch of different instruments across a bunch of different platforms that are all taking measurements to tell you different pieces about how the Mars climate system is working, particularly in the atmosphere, and then how ice is behaving between the atmosphere and the surface. And these instruments, if they were all on one mothership, would not work nearly as well. There would be a lot of limitations with the different instruments operating simultaneously. Some of them wouldn't really get good data if they were in one orbit versus the other. So this is a way to maximize the amount of data that you're returning from a mission. And in the case of something like the outer solar system, you could send something like this to try and get the most amount of data, taking advantage of the small launch windows that you have and the extremely long time periods that you have to wait for your missions to get to the outer solar system. You're still going to have some trade-offs here and there in terms of the quality of the data and what you can do, but this does open up some options there. And if you're interested in reading more about this mission, there is this mission concept. There's an LPSC abstract from this year that you can find online. Asteroid mining is probably the next biggest thing people tend to think about when they think about the commercial space sector, other than maybe in launchers. And the mining sector is interesting in that on Earth, it's one that already understands the reality of a large upfront cost for long-term gains, because setting up mining operations on Earth is never a cheap or trivial process. A lot of the mining things that have been proposed for asteroids are ice mining for propellant manufacturing, radiation shielding, and drinkable water, obviously. Or in the case of some asteroids, rare earth minerals, particularly platinum group metals. Caltech at one point estimated the cost for an asteroid mining mission at $2.6 billion, which sounds like a lot. I mean, that's the cost of the Perseverance rover. But the cost to set up rare earth metal mines on Earth is about $1 billion. So it's, like I said, it's not an inexpensive process as it is. And this was really popular across the last decade with promises of these huge payoffs of, mining platinum out of asteroids worth trillions of dollars. Not a lot of discussion about the fact that if you start mining asteroids for platinum and it's no longer rare, what happens to the price of platinum then? But it was something that made Silicon Valley investors quite excited. And so some companies really jumped on board with this. Unfortunately, there's been a huge bust in terms of the asteroid mining sector. Probably what most people would call the two main players in that sector, Planetary Resources and Deep Space Industries, have both essentially gone out of business. They were bought out by non-space mining companies and basically dismantled at this point, because investors in the companies, while they really liked the idea, a lot of investors in Silicon Valley are looking for returns in less than 10 years. And when you're looking at asteroid mining, you're looking at like 15, 20 years before you start to see anything really. But the technology developed for asteroid mining can have larger applications in space exploration. Deep Space Industries, for example, developed a water-based propulsion system that could still have applications beyond their mining tech. Planetary Resources developed a hyperspectral imager to do prospecting of asteroids. But whatever you're going to do, you need some kind of short-term business plan to generate revenue toward that long-term goal. And that's something that SpaceX seems to have done pretty well. For example, the end goal for Elon Musk has always been he wanted to go to Mars, but going to Mars directly is not financially viable unless you just happen to have a ton of money. And Elon has a lot of money, but not enough money to just send his own missions to Mars, obviously. So he's working with NASA to develop these technologies, getting contracts for things like Falcon, developing things like Starlink, using these as the way to fund his future goals. So any of the new space technology that's being developed, if it's going to take a long time, needs some way to be sustainable until it reaches that point. The one big benefit that did come out of all of this, though, is that the policy framework for off-world resource mining was established in the middle of all of this boom of asteroid mining companies. And so we have something in place for when things like in situ resource utilization really become a thing, moving beyond the Earth. So, sort of summarize everything, some of the advantages of the new space sector beyond Earth when we're looking at things like deep space exploration missions are that you have the opportunity for shorter instrument and mission development timelines, which can reduce costs and open up, hopefully, more options for more missions to more places, as I said before. I hope that it also leads to an innovation in instrument design and possibly moving away from so many heritage requirements because it might hinder innovation. You tend to see, for example, I'm from a camera background, so most of what I know about on planetary missions are cameras. But you tend to see a lot of heritage instruments that are cameras that are directly adopted from one mission to another. You see the same vendors popping up again and again, which doesn't really give anybody else a chance to jump in the game. And it doesn't really push for innovation if those particular vendors know that they're going to be selected over and over again. And if they're just reusing things off the shelf that they already happen to have based on designs that are, maybe even 10 plus years old, to stick to the heritage requirements, it might not necessarily be the best instrument for the science that you want to do 10 years later. And it might not necessarily even be the best or cheapest technology available anymore because it hasn't changed in 10 years. And just re-emphasizing again, lower launch costs, lower mission costs, shorter timelines, the opportunity for more missions to more places. And I think that's what we all want. We don't just want to see all the money going into Mars missions and moon missions. We still have so much left to learn about the rest of the solar system. And so I really hope that adopting these agile aerospace type approaches and technology and really rethinking the way that we approach mission design and not wanting everything to necessarily be absolutely perfect, but being okay with good enough if that's all you really have the option to get. Maybe we can get more done in the solar system. So under this framework, what becomes the role of government in space exploration? I would argue developing the infrastructure needed for the commercial space sector to thrive. And this isn't necessarily physical infrastructure, but something akin to the development of everything that Amazon needed to be successful, for example. Jeff Bezos has said multiple times, there's no way that Amazon would have been successful as a company if things like the internet and the highway system and the postal service didn't already exist. So these were things that they were able to take advantage of to create a company that became financially successful. And this is what we need for space as well. Policy and regulatory framework are big ones. Since this sector is so new, there's still a lot of either missing or loose guidelines in some places, to the point where some companies are asking for this framework to be put into place sooner rather than later, so they can make sure that they're operating under the right guidelines, so that something doesn't change on them in the middle of their business operations. And this is something that the government can put in place to make sure that things are favorable to commercial companies operating or commercial companies operating in close collaboration with the government on these space exploration projects. Offering funding opportunities. So there are programs right now like the Small Business Innovation Research Fund, SBIR, and the Small Technology Transfer Research Fund, or STTR, which support collaborations between universities and private companies in the space sector, and others as well. There are programs under SBIR and STTR across a number of government agencies. The problem is these funding opportunities are quite small compared to how much it costs to develop technology for space. So it might not be sufficient the way it's set up now to really spur innovation in these areas. But having that there is a really good way to get people to start applying their knowledge and expertise towards solving problems in space. There's also a need from the government to provide incentive for innovation. So one example I could think of is announcing the goal of a NASA flagship mission with commercial partners. Obviously, looking at the huge diversity in the array of choices that they picked for the lunar lander options for Artemis is one good example. Just looking at those three pictures side by side, the renderings, you can tell that these are three very different architectures that they've decided to fund. But taking that a step further and saying, okay, we're going to send a Cassini level mission to Uranus, but we'd like to see what the commercial sector thinks they could provide in terms of science instruments or propulsion or power or something like that. That could be a really great way to spur innovation on that side and give some incentive to develop new technologies, even if it's to an area that itself is not commercially viable. You know, we're not going to see human missions to Neptune for a very long time, I don't think. And we're not going to see necessarily a commercial return on sending a mission to a place like Neptune or Pluto, unless NASA puts some incentive there by offering money to buy commercial instruments to use on these things. So there's an opportunity here for a really great partnership, not just in the human space sector, but in the planetary science sector as well, in terms of collaboration between the private sector and scientists, academia, industry, government, across all of these things.